here. Okay. Before that, while that's coming up, let me go over last time you were here this announcement, because today's the last day to apply. Okay, I don't think probably either one of you are wanting to apply, but you may know of someone who might want to apply. This is line worker training going to be offered here at the college as part of our workforce development. This is in partnership with Alabama Power and various utility and contracting companies. So if you know of anyone who might be interested in this, the applications are accepted through today, last day. All right. The training duration will be from June the 8th through August the 14th. Classes will meet from Monday through Friday in the summer, 8 to 4. That's a 9-week program, 8 hours a day, probably about an hour or so for lunch. The program tuition is $4,150 plus fees. Now, the fees include books that you might need for it. Don't know how many that would be. PPE, which is personal protective equipment, okay, that you would probably either have to buy or rent, okay. Part of the training is going to include getting a commercial driver's license, because you may have to be driving these trucks around with cranes on them, and that requires a commercial driver's license. And so the commercial driver's license requires a physical. That you'll have to pay for, not part of the program. There also may be, and probably will be, some permits, licensing, and exam fees, depending on what permits, licenses, and exams you're going for. There's multiple ones you can do. But the good news is scholarships are available. I think they're hurting for people like us. They want needing to hire more people to do this kind of work. It's line worker training program, as in Alabama Power, the other power companies, phone companies, and contractors for them. Okay. Now, the program outcomes. People who complete will probably be guaranteed pretty much an OSHA 10 certification, at least if you pass the licensing and permitting fees or exam fees and stuff, exams. That's Occupational Safety and Health Administration 10 certification. When you complete, you probably will also have a commercial driver's license, which is valuable in itself. You will have been trained in cardiopulmonary resuscitation, CPR training, and you will have developed and learned basic line worker skills. Big time. All right. If you need information on this, or anyone you know may need information on this, at Washington State Community College, the Office of Workforce Development, Dr. James Gray is the Workforce Development Manager. And I have his phone number and his email address. And the phone number indicates he's here on this campus. It's a 3519 number, and most of the threes, like mine, is 3449. So most of the numbers on this campus start with 3. My guess he's over here in Ethel Hall building. I don't know that for sure, but my guess would be there. He may be over on the other side, on the in the Mill South building, but he's somewhere, I think, on this campus. You could also contact Mr. Tommy Hobbs, who's the Assistant Dean for Workforce Development, and I'm almost certain he's over in Ethel Hall building. Now that I think about it, I say Ethel Hall, it could be Vesselnier building, which is just next door. So one of them could be over there. I think probably Dr. Gray could be. Now, in order to apply, you have to go click on a link, and it's an Eventbrite link, and this one has the name in it, Pre-Apprentice Power Line Worker Application Tickets. So, if you know someone who's interested, today's the last day to apply. they need to get this done today. I don't know if payment is due today or not. I imagine you have more time on that, but the application is due today. Now, the one other announcement, I can't remember if I told y'all this on either Monday or for you Tuesday. I'm required to go to a mandatory meeting on Friday down in Opelika, Alabama. And we will be gone. The meeting goes from 9 till 2, and that means we're going to have to leave here somewhere around 6ish or so to get there. We're going in a van or something like that. So I think we're going to be leaving around 6 and getting back probably around 5, okay? Could be a little earlier than that. So in other words, my office hours for Friday are gone, okay? I'll be on the road or in Opelika all during my normal 8 to 12 office hours on Friday. Won't be anywhere close. So if you needed anything, I need it today or tomorrow because I won't be around on Friday. All right, any questions about anything we've covered, anything we've done, anything such as this? Okay, we're in chapter 12, which is vector value functions. Just got it started last time, and we're in 12.1, vector value functions. The chapter title and the section title are exactly the same, and we had done through up to example 2. Example 2 is sketching the space curve, and you can go to larsoncalculus.com for an interactive version of this type of an example, and you might be able to see them sketch it, in person. So you may find it a little more satisfying than watching me do it. It says sketch the space curve represented by this vector value function, and this is r of t, vector function, because it's bold R there, of t is equal to 4 cosine ti plus 4 sine tj plus tk, and this is going from 0, t is going from 0 to 4 pi. Okay. So, again, I don't draw these things well. I don't even pretend to draw them well. I can't get my pen to activate. Yep. It has now. So let's just say here is your z-axis, your y-axis, and your x. X, y, and z. Okay? Now, let's start. Well, let's tick off a few points. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay? Sketch the space curve, okay, represented by this. Let's let t be its initial value 0. What is cosine of 0? 1. 4 times 1 is 4. So the x-coordinate is 4. The y-coordinate, t, when t is 0, sine is 0. And the z-component is 0. So here is where we began on the positive x-axis. This is negative x back this way and negative y over here. We're not going in negative z, so not going to even mess with that. All right. Let's go to what I would consider the next convenient place. T is equal to pi halves. Okay? Now, yeah, I know. I was just looking at this. In the book, it's t is going to 4 pi, and on the slide here is 2 pi. Okay, so we'll go to pi halves. All right. Cosine of pi halves is, so the x-coordinate here is 0. Sine of pi halves is 1, so this is going to 4 on y, but you're going up 1 in the the z direction. So that's going to be right about to here. Okay. Now, this is following a circular path. I don't draw circles in space well, okay? So bear with me here. It's doing something like that, okay, going up to a certain point here. All right, let's go on to pi. When t is equal to pi, what is your cosine of pi? Oh, let me tick off the points back here too, and over here. Okay. T of pi is, when t is pi, cosine is -1. So this will be a -4 on the x, and of course cosine pi, sine of pi is 0, so your j component would be 0, but your k component will be 2 up. So here you've gone 2 up. I'm going to try to go 2 up. Something about like there. Okay? So now you've gone from here, and this probably bulges out more than what I'm drawing, to something like that. Somewhere in there. Okay? When t is equal to 3/2 pi. Okay? Cosine is 0. Sine is -1, so 4 times that would be a -4. And now you're up to 3. I've been going wrong on this. Sorry about this. I've been going t. I hate to do this, but I'm going to start over with my drawing. Yeah, I know. That's what I said. I was doing pi's, and yet my t's, when I got to that, I was doing 1, 2, and 3. So that's why I'm starting over, okay? Because I need more z space. And since we don't have any, let's see, this is x, this is y, this is z. Still not going to be sure this is work, because I'm going to need 12 plus nz. And I'm really going to have to compress that. So if this is 12, this will be 6, this will be 3, this will be 9, this will be 1 and 2, 4 and 5, 6, 7 and 8, 10 and 11, something like that. So let's do 1, 2, 3, 4, 1, 2, 3, and 4. And then do our negatives back here. 1, 2, 3, and 4. And our negative over here. 1, 2, 3, and 4. Okay. All right. This was 4, 0, 0. This was pi halves, which is 1.5 approximately up. So that would be right about here. Okay. Now I say 1.5. It's a little more than that, but that's as close as I'm going to mess with. So you're doing something like this. Then the next one is at pi, which is 3.1. So it's -1 here, and we're going up. And this still is going to be way off scale. I can't do this well, okay, because we're going 3 up from here, 3 up from there would be something like there, I think. Okay, so this is going here, and this is bulging out something like that, I think. Okay? Then when we're 3/2, we're over here again, but we're going 3/2 pi would be about 4.5, wouldn't it? 9, halves, about 4.5 or better than that. 1, 2, 3, 4.5, something about like here. Okay, so this is coming around to here. Okay, the next one, 2 pi, which is where they were going to have a stop. I wish we could. That will be, we're back over here again, but now we're up about 6. 1, 2, 3, 4, 5, 6. So we're here. This really.
For t is equal to pi, should that point be later?
Oh, you're, no, okay.
Okay.
Okay, you mean the one back here? This one back here? You see, you have to be 3 up from here. Because here's your XY plane. So you're back there and you're 3 up from there. It probably should be even higher. Okay? And here you're up from this one. And now you're up from this one here. And for the life of me, I can't make that come around and do what it's supposed to. Here's what we're supposed to have. I'm going to try to do this best I can. Okay, there's your circular base. Okay, and then this is going up from here, and up from here, and up in every dimension from there. Okay. And it's going to be a circular base, and this is going along that thing. So this is somewhere back on here, coming back around here and going up. It's a spiral going up. And I'm just terrible at drawing this stuff, okay? You folks that are going into engineering, get used to drawing. Of course, you're probably going to be using CAD and other things like this, but if you have to do engineering graphics the way we used to have to do it, okay, my hat's off to you. But anyway, that's what we've got going on. And I don't have enough room on Z because, you see, I'm supposed to be able to go up way higher here, because this is just one time around. Next time it's going to be even higher, and I'll be off scale here or coming back in here. So the next time it would come through to somewhere on here. 12 up from here. So it's a mess, but you get generally the idea of what's going on here. I'm going to stop now while the stopping's good, but you get the idea, okay? I hope so.
Required to draw pictures like this on the test?
Oh, you absolutely, no. If I have to grade it, no, you're not going to have to draw it. But I'm not saying that in the future. Now, you may skate by, but the engineers, you're going to be drawing. Maybe not this, but stuff almost, well, maybe even worse than this. But you won't be sketching by hand, I don't think. I hope not anyway. Okay. So let's see how they do it. From the two parametric equations, you can obtain the x squared plus y squared is equal to 16. Yeah, because sine squared plus cosine squared is 1. Okay. That means you have a curve that lies on a circular cylinder, radius 4, centered around the z-axis, and to locate the curve on that, you use the third parameter, climbing. It's a helix going up that curve. This is how it looks. And this figure, note that as t increases from 0 to 4 pi, the point spirals up. See, now they have 4 pi. Previous slide, they were 2 pi. I don't know how they did that. Spirals up the cylinder to produce a helix. And you see, this is where I was having problems, it's going here, and then it's the way I had it drawn, a little more angle here. It was coming down and then going back up, and it just got really hard to draw. In fact, even here, I don't buy that this one looks like this and this one looks like that. This curve down here needs to look more like that, I think. Yeah. Or that one needs to look more like this, because it's the same perspective. So I don't see how, but even they're having trouble drawing it, okay, and I'm sure they have some sort of package to do so. But it's a circle of radius 4, a cylinder on that circle of radius 4, and you're going up the cylinder in a helix. And here's Josh. So we're only missing Ryan. Okay. So there's what we've got. I'm just going to look here and see, does this point look like it's directly under that? I guess it could be. Okay. What I don't see is how this looks like this coming around here. It looks like this coming around there. It seems like this one needs to look more like that, or that needs to look more like that, because those are basically parallel to each other. But even, my point is, it's even hard for them to draw and make it look realistic. But you're going up a tin can. That's a helix. Any question about that? Look at it on larsonCalculus.com, and you'll probably see that they may actually draw it for you, and you might see something better than this. They have a little note on the side here. In 1953, Francis Crick and James D. Watson discovered the double helix structure of the DNA. That's two of these helixes going around the same axis, but apart. Let's say the other one may have started here and gone up inside this one, and then the chromosomes link between the two DNAs, and they link in certain patterns going up. It's pretty interesting stuff. All right, any questions? Don't ask me to draw anymore. Okay. Oh, here it is. Real life example of a helix is shown in the drawing below. This is the supposedly the structure of this, and I don't know, some of you may have had biology more recently than I have, because they didn't know this back then. Well, they did, but it wasn't being taught in high school, what the pairings were that you connect. They have letters they represent, and those represent the chromosomes and the various combinations you can have. Okay, double helix there. All right, moving on. Says, I think we're moving too fast. Yes, we are. We got to go back and do example 3 and 4. In examples 1 and 2, you're given a vector value function asked to sketch the corresponding curve. The next two examples address the reverse problem, finding a vector value function to represent a given graph. Of course, when the graph is described parametrically, representation of the vector value function is straightforward. So here's sort of kind of an example they're giving. This isn't, I don't think, the one we're going to be doing in example 3, but here it is. What if you had x is equal to 2 plus t, y is equal to 3t, and z is equal to 4 minus t? Okay? Then your vector valued function, r of t, that's your parameter, is 2 plus t I plus 3tj plus 4 minus tk. Okay? That's all you do. You know, if you know the parametric equations, it's simple to write the vector. All right? Now, example 3 is coming up here. Now, I'm afraid I'm going to have to draw the graph, but this is a simple one. Okay? Relatively speaking. Okay. So represent the parabola y is equal to x squared plus 1. Okay, by a vector value function. And guess what, team? You don't have to draw the graph. Okay? You know what it looks like, don't you? It's basically the parabola. But since it's a plus 1, you start here, and then you go up 1. So it's not 1, 1, but 1, 1 from here, 2, 4 from here, 3, 9 from here. You draw your parabola like that, only you elevated it 1. Pretty simple thing. Here, this is fairly simple itself. Okay? Represent the parabola y is equal to x squared plus 1 by a vector value function. Here's the clue, the key. Okay? Pick the most complicated, the variable that has the most going on with it. I'd say that's the x. Let that be your parametric value. Let x equal t. Then, pretty easy to get what y is. What is y? Anybody? T squared plus 1. So here's your vector value function. Favorite name, r of t is equal to ti plus t squared plus 1 j. That's all there is to that one. Okay? But notice here they said represent by a vector value function. Guess what? There's an infinite number of vector value functions you could put in there to represent the same parabola. Okay? This one will have a definite orientation as t is going from 0. This would be 0 on I and 1 on j. Sure, that's 0, 1. The next point would be 1, 2. Okay? So it's going this way. If you had chosen negative t's, it would have been coming down like this. So there's your parabola that way. The t would be going from negative infinity to positive infinity, being drawn left to right. Okay? That is 1. Okay? Had you chosen, why would you want to? Negative t as a parameter, x equal negative t, then it would have started over on the right-hand side and gone right to left. That would have been the only change. And you could have done several other parameters, and they did. So that was the easy one, okay? That's the one that is a vector value function that represents that parabola, the one they gave. Now, let's do example 4. If I can get my cursor back. Okay. Erase all this. Sketch the space curve C, sketching again, represented by the intersection of the semi-ellipsoid. I'm loving this already. Okay. Sketch the space curve C, represented by the intersection of the semi-ellipsoid x squared over 12 plus y squared over 24 plus z squared over 4 is equal to 1. And this is for z's greater than or equal to 0. So you're only the top half of this ellipsoid. Okay. And the parabolic cylinder, y is equal to x squared. You talk about something fun to draw. Yes, okay. Then find the vector value function to represent the graph. Okay. Oh, how I wish they would have shown this one so I wouldn't have to. Okay. Let's sort of see what we can do about sketching this thing. Here's your x, your y, your z. Z, that's a pretty ugly z, okay. I'm going to need a negative x back here. I'll need a negative y over here. We won't need any negative z's, okay. First, your semi-ellipsoid. If I could get someone to do a square root of 24, that's going to be something just under 5. 1, 2, 3, 4, 5. So let's just say it's right about there. Okay, negative 1, 2, 3, 4, 5 to right about there. That's your y axis. Okay, your x is going from square root of 12 is between 3 and 4, so let's just say 1, 2, 3, 4. Let's just say right in here. Not that I know where it is. Oh, perfect attendance today, if a little tardy, but okay. Better late than never, I guess. Okay. All right, good. Perfect attendance all week, team. Way to go. Okay, so your x is going plus or minus something between 3 and 4. 2, 3, and 4, somewhere here. And z is going up 2. Okay. So, your ellipsoid down here is going to be here, 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 and there. From here it's going through this point this way, from here it's going through that point this way. There's your ellipsoid, if you can imagine it. All these level curves here parallel to the xy plane would be little ellipses going up toward the peak there. Okay? Now, okay. Now, the parabolic cylinder, y is equal to x squared. I'm going to draw it in the xy plane to begin with. When x is 1, y is 1. So it'll be somewhere about right here. And minus 1, 1 would be somewhere about here. And 2, 4 would have been out here somewhere. Let's see, now it's 2, 4 on that. It may be. It may be right about there and there. I think it is. Okay? Now, that's in the XY plane. But you got to be on the, and I'm going to try to sketch that parabola on the XY plane. Something like that. Okay? But we got to project up onto the ellipsoid. So the projection up here is going to be at the top, and it's going to come around like this, but be coming down to there, and around like this, coming down to there. Now that's a pretty lousy representation of it. You'll see a little bit better one in your book, if you're looking at your book. So yeah, the points are going to be 2, 4, 0. This is minus 2, 4, 0. And this one up here is going to be 0, 0, 2. Okay. Now, that's the drawing, and the strange thing is, in this case, this is almost the easy part. It says, then find the vector value function to represent that graph. I think I'm going to go with a different color here so you'll know which one I'm talking about. Pick me a color other than black. Red, okay. This is the ellipsoid I'm talking about. Something like this. I mean the curve that we're talking about on that ellipsoid. Okay. Now, here's what I think I'm going to do on this one. Okay. I'm not absolutely certain this is the best way to go, but I think it is. If these two have to be true, let me go back to black, these two have to be true, then this would also be true. That x squared over 12 plus y is x squared, so that would be x to the fourth over 24 plus z squared over 4 is equal to 1. Okay. I'm not sure that's extremely helpful, but it may be a little bit. Maybe a little bit. Okay. And then I'm going to try to do this. Z squared over 4. Okay, I'll do it one step at a time. Is equal to x. Okay. Sorry. I'm not sure this is the best way to go, but it's one way you could go. 1 minus x squared over 12 plus a minus x fourth over 24. Okay. And then, to get rid of that over 4, let's say z is equal to, z squared, is equal to 4 minus x squared over 3 minus x to the fourth over 6. You see what I've done there? Just multiplied everything on both sides by 4. Okay, now I'm close to having something that I can fiddle with. Okay? And the next step would be to take a square root. But that's going to do a plus or a minus. So let's try to do it with, well, let's just see what happens if we say let x equal t, because that's everybody's favorite parameter. Then from here we get y is equal to t squared. It has to be true, right? And then let's say, oh, I didn't have to do most of that, did I? Sorry about that. Live and learn. Okay. I want to erase most of this. Let's do this then. Let's just plug in what we've got here. X would be t squared over 12, if x is equal to t, plus y is equal to t squared, so this will be t to the fourth over 24, plus z squared over 4 is equal to 1. Okay? And then basically you can solve for z. Easier said than done. So I think maybe I should have tried to... No, they did the same type thing that No, they were proceeding the same way I was, except I multiplied by 4, they didn't. Okay? They kept it over 4. So let me theirs does look like it's a little bit easier way to go. You can do this way, but I think theirs is a little easier. Let me erase some things here. Oh, that wasn't it. That's what I wanted to keep. Sorry about that. I think I've erased part of my graph too, but that's okay too. This is the part I wanted to erase. Okay. Let me write this one back in. This was z squared over 4 is equal to 1 minus, and I said x squared over 12 plus x to the 4th over 24. Okay. We had that. Okay, and now rather than multiply by 4, and I think I could have done the same thing. In fact, now that I think about it, I believe that what was smarter. Let me go back here. I like what I was doing more. Z squared, someone got that down, is equal to 4 minus x squared over 3, was it? I think that's a minus, not a plus. I put a plus in there before, and I was starting to again. Minus x 4th over 6, right? Now, on the right-hand side, what I'm going to do is use least common denominator of 6. That would be 24 minus 2x squared over, okay, 2x squared minus x to the 4th. All that's over 6. Okay? Can you follow what I'm doing here? I got my least common denominator of 6, which made that a 24, that a 2, and that. Now, can we factor this? I sure hope so. This will be 6 plus x squared times 4 minus x squared. Let me see if I did that right. Minus x to the 4th minus, yeah, I believe that's right, isn't it? Over 6 is equal to z squared. Now I'm real tempted to put the 6 back here so I don't have to mess with that anymore. Maybe not. We'll see. Okay. Now let's go back and do what I was starting to do before. Well, I still haven't seen quite how they're going to manage that. Oh, I see. They are doing. Oh, of course. Sorry about that. Z is positive here, remember? We're not doing them much. So we don't have to do plus or minus Z. Only the plus Z. So from what we had here, forget the 6, put it back there, and what we have is Z is equal to the square root of 6 plus, that's a 6, plus, and remember your x was t, so it was t squared times 4 minus t squared over 6. That's what your z is. This is what your y is. This is what your x is. Wherever right. No. I wrote it somewhere. I must have erased it. Okay? X is equal to t. Okay? So, our vector value function, let me erase a bunch of stuff then that I don't need. I don't need this, I hope, and this, I hope, and this, I hope. I don't even think I need that point anymore, so I'm going to get rid of it too. Not that it's wrong, but I just don't need it. Here's our R of t. Representing that red curve there, R of t is equal to ti, because x was t, there it is, yeah, well, I wrote it there, plus t squared j plus, and here's the fun one, the square root of 6 minus t squared times 4 minus t squared over 6. Okay. They don't have to be things that are pretty, easy to do, or anything else. Just get it into a parametric equation. Okay? And that's a parametric equation. So R of t is equal to ti plus t squared j plus the square root of 6 plus t squared times 4 minus t squared all over 6 times k. Oh, we need limits, don't we? Where are our x's going from? X's are going from minus 2, and I did need that point here. This point here was 2, 4, and 0. And since the t is your x, then the limits on this is minus 2 less than or equal to t less than or equal to positive 2, because it starts there and goes there. Okay? So you always need to put your limits of your parameter, your parameter in there. And that's indeed what we've got going here. Okay. Aren't they fun? Okay. That's probably the worst you hope to see. Until it's test time, of course, then we'll come up with something that'll be even worse. Okay, so that's example 4. Any questions on that? I know that was a long, circuitous, stop and back up and try again type process, but that's how we got it. I was worried about what to do with the plus or minus, and I completely forgot t is greater than 0. That right there. That eliminated that worry. All right. So let's move on to questions? Oh. Okay. Limits and continuity. Now, hopefully we're going to go through this pretty quickly. The limits are always a lot of fun, aren't they? Definition of a limit of a vector value function. If R is a vector value function, notice it's a bold R. So let's say R of t is equal to some f of ti plus g of tj. This is in 2 dimensions in a plane right now. Then the limit as t approaches a of R of t would be the limit as t approaches a of your f of t. That's the only place where the t shows up. So and that would be your I part, and limit as t approaches a of g of t, and that would be the j part. Provided that f and g both have limits at t as t approaches a. If they don't, you can't take a limit of the vector value function anyway. Okay? If it's in 3 space, vector value function is R of t is f of ti plus g of tj plus h of tk. Same deal. Limit as t approaches a of R of t would be the limit, and for some reason they chopped off the bottom bracket here. Limit as t approaches a of f of t I plus limit that whatever that limit of g of t is t approaches a j. Whatever the limit is h of t as t approaches a times k. Provided now that f, g, and k
H, I'm sorry, all have limits as t approaches A.
If they don't, you can't make a limit there. So, assuming they do. All right. If R approaches the vector L, R is a vector, so now the limit has to be a vector as well. Vector L, as t approaches A, then the length of the vector, R of t minus L, has to be approaching 0, as R is getting closer to L. It has to be, the length has to be approaching 0. That is, the magnitude of R of t minus L has to be approaching 0 as t approaches A. Because, you know, they're getting closer and closer as t is, R of t is approaching L, so they're getting closer and closer together. Okay? Now, here's what it means. Here is our R of t there, and this is your L here. And as t is approaching A, R of t is getting closer and closer to this L vector. Okay? Here's your R of t here, here would be R of t later, R of t later. So this R of t minus L, this is what's getting closer and is approaching 0. And that's what this is showing. As t is approaching A, R of t out here would be somewhere here, here, here. And then the difference of these is getting less and less and less until it goes to 0. As t approaches A, R of t is approaching the limit L vector, and for the limit L vector to exist, it's not necessary that R of A be defined or that R of A is equal to L, it's just that that's the limit. Okay? R of A may not even be defined, or it may not equal L, but it's going to be approaching L. Okay. Just like we did with limits before. So this next definition extends the notion of continuity to vector value functions. Vector value function R is continuous at the point given by t equal A when the limit of R of t exists. First, it has to exist. It can't be going up to infinity or something like that. That limit must exist as t approaches A. And not only does it exist, but the limit of R of t as t approaches A is R of A. On the last one, we said it didn't have to exist. Now we say it does. And that's what it must be. The vector value function R is continuous on an interval I when it's continuous to every point on the interval. Okay? They haven't said anything about the endpoints yet, so let's just assume that that means they're continuous at the endpoints as well. Okay? Because they said on an interval, usually that will include the endpoints. Not that it really matters that much now. So here's what it says. Discuss the continuity of this vector value function at t equals 0. Okay? First, is each of these functions, t, a, and a squared minus t squared, do those all have limits as t approaches 0? What would this one be? I'm saying limits, and that's true. Is t continuous? Yeah, it's a linear function. Okay? A, it's a constant function. It's continuous everywhere. Is this continuous at t equals 0? Yeah, okay. That would be a squared as t is approaching 0. So if all those exist, then R of t exists there, is continuous there, so I don't see there's any problem anywhere. Have they even written that right? That seems like it's way too simple, okay? I shouldn't say that, but let's see. As t approaches 0, the limit of R of t would be the limit as t approaches 0, which would be 0, okay, that's right. This would be a, and this would be a squared. So yeah, I don't see an issue anywhere. Okay? Now, because R of 0 is also that, you can conclude that R is continuous at t equals 0. Okay, that's sort of a duh type problem. I was looking at this graph over here, which really looks horrendous, but who cares? The point that we're interested in down there is as t approaches 0, you're approaching something that has no x-coordinate. It's that parabola there. You don't see it. Let's see. Sorry. By similar reason, you can conclude the vector value function R is continuous at all real number values for t, because whatever value you put in it, and here it is. Here's the graph. For each value of a, the curve represents a vector value function. In example 5, here it was ti plus aj plus a squared minus t squared k. Where a is some constant. Okay? Now, this is a parabola, and you can think of each parabola as the intersection of a vertical plane, y is equal to a, which is exactly what we've got here, to the hyperbolic paraboloid, which was y squared minus x squared is equal to z. Okay, because z is equal to a squared minus t squared, which is y squared minus x squared. Okay, and there is that hyperbolic paraboloid. Okay, and these are the various values for. Remember, a is a constant. Okay, so if a is 0, there it is there. Your j component is just a, which is 0. When a is equal to, say, 2, this is the parabola. Okay? Here. Minus 2, it would be over here. Because you see, a is a constant. So y is equal to a is right there, or here, or here, or here, or here, you know, or anywhere in between. That is the a, and then you have the parabolas that fit this bill here. So it's continuous everywhere. You can just keep on carrying it out, and it will still be continuous everywhere. Okay. Whoa. All right. They skipped example 6. Let's see what we can do with example 6. Determine the intervals on which the vector value function R of t is equal to ti plus the square root of t plus 1 j plus t squared plus 1 k is continuous. We want the intervals where that will be true. What's the interval measuring? Interval of what? What is the intervals concerning? Let me give you a hint. It's not x, y, and z. Intervals of
I, J, K.
t, your parameter t. That's what we're looking for, the intervals of t, which will be continuous, yeah. This vector function will be continuous. And what we always do is look for limitations. Any limitations here? No, all real numbers. We find that. How about here? No. How about here? Whoops! What's your limitation?
Can't be negative 2.
You're right. It can't be anything. In fact, the quickest way to do this, okay, quickest way to do it, it's under a radical. And that means what's under the radical, t plus 1, has to be non-negative, greater than or equal to 0. Subtract 1 from both sides. T has to be greater than or equal to negative 1. It can be equal to negative 1. Square root of 0 is fine. Okay? But it can't be anything less than negative 1. Like you said, negative 2 won't work. So anything greater than or equal to negative 1. So that is it. So what was the question? The interval? The interval would be negative 1 to infinity. That's where that would be continuous. Okay? This is no problem there. That's no problem there. This has to be on that. So that's it. Make sense? Okay. Not nearly as bad as they can make it sound like it is. Homework exercises 12.1. Do any of the odds 3 through 9? They're all at by the way, I don't usually say this, but there's always, I hardly ever say it. There is a concept check there. Look at the concept check. Read through it. Make sure you understand what it's talking about. Once you're confident you know what it is, or if you're not, go back and look in the section and find that, refresh your memory on it, then do your exercises. Any of the odds 3 through 9, they're all at Calc Chat. 3's at Calc View. 11's at Calc Chat and Calc View. 13 and 15 are both at Calc Chat. 17's at Calc Chat. Try to do all 4 of 19 through 22. Now, only 19 and 21 will be at Calc Chat, but try to do all 4 because you should be able to sort of pick up and recognize what these drawings are. This is what you need to do rather than have to draw them yourself. Okay, so do all 4. Okay, then do any of the odds 23 to 29. They're all at Calc Chat. 25's at Calc View. There you can see them doing it. Any of the odds 31 to 37, they're all at Calc Chat. 31's at Calc View. 39 should be at Calc Chat. 41 should be at Calc Chat. Either 43 or 45, both of them should be at Calc Chat. Any of the odds 47 through 53 are at Calc Chat. 51's at Calc View. Any of the odds 55 through 61, they're all at Calc Chat. 55's at Calc View. 63 should be at Calc Chat. 65 through 69 should be all at Calc Chat. 67's at Calc View. 71 through 75 are all at Calc Chat. 71's at Calc View. You can explore or think about doing 77 and or 79. They should be at Calc Chat. If they're not, don't mess with them. 81 is an interesting looking problem. That should be at Calc Chat. There's a couple proofs there, 83 and or 85. You can do those if you wish. Especially you math majors, you might want to give those a look. 87 should be you can think about doing that one. 89 should be at Calc Chat as well. Now, there's a section project here. You don't need to do it, but it's talking about the Witch of Agnesy, okay? Which is a terrible, perhaps Freudian slip, okay? Historical. This, I can't think of her first name, Agnesy, was a brilliant mathematician who happened to be a female back when we didn't have any female mathematicians. Women weren't even educated to be, but her father was quite something and recognized her brilliance, and he'd self-taught her, and she became, I mean, just amazing, okay? Floored everybody. They wouldn't give her a degree or anything, but
she could just run circles around just about anyone else on the globe at the time in mathematics. Well, in their little world anyway. And she came up with a curve that was a pretty interesting curve, something no one else had ever thought of. And she was Italian, and I can't remember what the deal was, either when they translated it from Italian to Latin, where they were supposedly all the scientific writing was there, and then someone else translated it to some other language somewhere along the line, what was supposed to have been a simple word like curve or drawing or something like that of agnesi, just by messing up a vowel or something, misreading or something, they translated it which I'm sure was just a slip of the tongue since she was a female. It just happened to turn out that way. There's nothing witchiness about it, but anyway, she would be a good paper topic if anyone's interested, or this curve and how it got completely screwed up in the naming of it, but it's still called that to this day. So anyway, that's section 12.1. Any questions on 12.1? All right, let's move on to 12.2. All right, and we go till
210.
2:10. Okay, so we got about 30 more minutes. No. Yeah, about 30 more minutes. Okay. So let's leave this slide and go to 12.2. By the way, 12 is a fairly short chapter, so let's we're making reasonably good progress on it. So don't be dawdling too much on your chapter 11 test. Okay. Slideshow from current slide. All right. Still in chapter 12, vector value function. By the way, the bottom right figure was one we saw in one of the exercises there. So we'll continue. 12.2 is differentiation and integration of vector value functions. And folks, this should go pretty quickly too. We will differentiate a vector value function and we'll integrate a vector value function. So let's start with differentiation of vector value functions. The definition of the derivative of a vector value function parallels the definition in real value functions, meaning scalar functions. Definition of a derivative of a vector value function. The derivative of a vector value function R is, the derivative of R is the limit as delta t approaches 0 of R of t plus delta t minus R of t divided by delta t. For all the t for which the limit exists. So if t is taking you somewhere the limit is not there, don't go there, okay? It's only good. It only has a derivative where that limit exists. If R of t does exist, then R is differentiable at t. If R prime exists, for all t on an open interval I, then R is differentiable on the entire interval I. Differentiability of a vector value function can be extended to closed intervals by considering one-sided limits for their endpoints. So that's what I was saying before. They're saying in an here they said open interval. Okay, so that means you're not including the endpoints. So you can't include the endpoints if you consider one-sided limits and the limit exists from that one direction. So differentiation of vector value functions can be done on a component by component basis. And if you recall back when we first started dealing with vectors, whenever that was, whatever chapter that was, I said way easier always to do things by components. Okay? And the same thing is here. So let's consider the function R of t is equal f of t I g of t j. If you apply the definition of the derivative, R prime is R of t plus delta t minus r of t over delta t. Limit is r delta t goes to 0. Then you just do the same thing. R of t plus delta t would be f of t plus delta t I plus g of delta t plus delta t j minus r of t would be minus f of ti minus g of t j. And then, and this is all divided by delta t, the limit of delta t goes to 0. Well then, group them. Group this with that, okay? And that's the I parts. Group the j parts together. And what do you have here? That's the definition of the limit of f prime. That's what f prime is. So f prime I plus g prime, that's the definition of g prime. So, guess what? If you're taking the derivative of a vector value function, take it component by component. Take the derivative of alpha t, that's with I, g of t with the j, h of t with the k, take the derivative component by component, it's done. That's all there is to it. Okay? This important result is listed in the theorem shown below, differentiation of vector value functions. If r of t is some f of ti plus g of tj, which we've just done. Here's another one of those vertical lines that just show up somewhere, where f and g are differentiable functions of t. They have to be. If they're not differentiable functions of t, you can't take the derivative of r of t. You just can't do it because those functions aren't. So the r prime of t would just be f prime of ti plus g prime of tj. That's all there is. If you're in 3 dimensions and all 3 are differentiable functions of t, then r prime is f prime I plus g prime j h prime k. That's it. Okay? Really easy. Okay? Theoretical. Okay, by the theorem. Note that the derivative of the vector value function r is itself a vector valued function. Okay? You can see from figure 12.8, I'm sure you can see from that, that r prime is a vector tangent to the curve given by r of t and pointing in the direction of increasing t values. So if this was your curve that r is describing, this is your r of t, different values of t, okay, and r of t is here, r of t plus delta t is there, then the difference between those, r of t plus delta t minus this, would be this vector here. And as the delta t is approaching 0, this is approaching r prime. That r prime is in the direction of increasing t because the t plus delta t was increasing. So that's the, and it's tangent to the curve. In space, so this has to be a vector as well. X, y, and z components of that vector. Hopefully that makes sense. So let's do example 1. I think you'll find they're not too bad. For a vector value function, r of t is equal to ti plus t squared plus 2j in a plane, just two-dimensional fact. Find r prime of t. Okay? Whoa, let me get my pen. Not that bad. R prime of t. What would it be? I plus 2tj. That's it. That is it. Okay? Oh, no, it's not it. Now we have to sketch the plane curve represented by r of t and the graphs of r of 1 and r prime of 1. So let's first do the plane curve represented by r of t. It's a plane curve, so all we have is x's and y's. So 1, 2, 3, 4, 5, 6, 7, negative 1, 2, 3, 4, 5, 6, 7, negative 1, 2, 3, 4, positive 1, 2, 3, 4, 5, 6. Okay. So, give me a t. Somebody? Okay, 1 will be fine. What would be r then? Say again? Okay, r is going to be a vector. Not, what would it be? T is equal to 1? It would be? Say again? Okay, that's a number. I need a vector. And T is equal to 1, what is R? Y'all chose 1, I didn't, okay. What would that be? I, that's yes in Navy speak, okay. Plus, there's your 3. That was the 3 you were talking about, wasn't it? I don't know where the 2 was, but that was it. So R of 1 would be I plus 3J. That would be it right there. This is R of 1. Oh, I'll put T. R of 1 is that vector right there. So you've already done the second thing they asked for, okay? But go on. I need some more T's. Give me another T. Even easier. 0, okay. Where would your R of 0 be? Y would be 2. 2J. That's all we got. 0, 2. Got it. Give me another T. Negative 1. And what would that be? Yeah. So here would be R of 0, and this would be R. This is going to get really messy fast. R of negative 1. So basically, to sketch the plane curve, do you see where this is heading? Give me another T. 2. What would that be then? 2I plus 6J. 1, 2, 3, 4, 5, 6. Just barely get that one on here. And then negative 2 would also be 6. What we got there? A parabola. But it's going in direction of increasing T. It's going from left to right. Down the parabola, then back up the parabola. There is your, that's the sketch of the plane curve represented by R of T. And then we've already plotted R1 of T. I didn't quite get the curve to go through there, but you know, you get the idea. Now we need to plot R prime of 1. Okay? What is R prime of 1? R prime of 1. I say 1 and write T. I don't know what's going on here. Okay. That would be, yeah, I plus 2J. Perfect. So I, and I'm going to choose to draw that at the point 1, 2, because wherever, 1, 3, 1, 3, there it is, 1, 3. Okay, so go right 1 for every 2 up, there would be something like this is R prime of 1. Keep writing T's. And it is indeed tangent to the curve at that point and pointing in that direction. But it is a vector, you know, with a given magnitude. I haven't figured out what it is yet, but who cares? There is a vector. Drawn at the point x, t equal 1, which is also x equal 1. Does that make sense? Okay. I know that's sort of messy. I wish I had drawn it further down. Want me to do that? Move it down so you can see better? Are you okay with it? You want it down? Okay. if I had been thinking ahead, which is not a promising thing for me to do, okay, do it down here, because this is, again, 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5. Okay. Okay. R of 0 would be 0i, and what was that? 2j, right here? 0, 2, and then this point was here, this point was here. 2, 6, and 3, 11. Yeah, I can't draw it. So anyway, here's the curve. Okay, heading in that direction. Okay, increasing t's. And the vector r1 would be this vector right here, r of 1, and this would be I plus 3j from the origin to 1, 3, right? Okay. Now, your r prime, which we already said would be I plus 2tj, and r prime, I'm going to do it again, no, okay, of 1 is going to be I plus 2j, right? Now, this time I'm going to choose to begin this one. I did this one at the origin. I could do this one at the origin too. I plus 2j would be right here, okay? It would be this vector right here. But I'm going to translate this and do it up here. I'll start it here, and then it's going 1 in that direction and 2 more in this direction. So this would be that vector. This is r prime of 1. But translate it up to the point where that is. And that indeed is tangent to the curve there, and that's its magnitude going in that direction. Does that make sense? Okay. Maybe a little clearer. All right. And if you don't like my drawing, too bad, but let's see how they do it. Can I erase this now? Okay. So differentiate on a component by component basis. That's what defines r prime. And you get I plus 2tj exactly like you did. Very good. From the position vector r of t, you can write the parametric equations, x equal t, y is equal to t squared plus 2. Not sure why you'd want to do that, but you can. The corresponding rectangular equation would be y is equal to x squared plus 2, which gives you your parabola, so maybe that's why they did it. But you could just plug in t's and see that. When t is equal to 1, you're there. R of 1 is 1 plus 3, I plus 3j, and r prime of 1 was I plus 2j. And when you draw those, here is your curve. Okay, that parabola we were talking about. Here is r of 1 going from the origin to that point. And here's r prime of 1 going from that point 1 over and 2 up. That gives you r prime, and you see that indeed is tangent to the curve at that point. Okay? And going in the direction of positive t's, of increasing t's. Does that make sense? Okay. The parameterization of a curve, okay, whoa. They're skipping example 2, so let's go back and get example 2 done. Okay. How are we doing on time? 10 minutes. Good. Example 2. For the vector value function r of t is equal to cosine ti plus sine tj plus 2tk, find each of the following. A, r prime of t. And it is a vector too, remember, so what would it be? Got it? Plus cosine tj. Got it? 2k. That's some type of bird or something, I think. Okay. The B part. What's r double prime of t? Say again? Negative cosine ti minus sine tj That's it. Done. C, that's yes in Spanish. What's r prime t dot product with r double prime t? Okay. Whoa, do you remember what dot products? That's a long time ago, wasn't it? What's the dot product? Second? Okay. Yeah. You multiply the I components together, J components together, K components together, add them up. Right? It's a scalar. Yeah, you're absolutely right. So what do you get? Okay, I think it's sine times. Okay, yeah. I would like to do sine t times cosine t I. Well, no, there's no more i's, remember? This is scalar. So sine times cosine, and that's not a dot product, that was just a multiplication sign there. Minus cosine t sine t, and 2 times 0 is 0. And guess what this comes out being? 0. Okay. Is it just this one? Is that going to be true for all of them? We'll see. Definitely for this one. Okay. D. What's the cross product of r prime and r double prime? Okay, did I hear an IJK being pushed around? I, J, K, what next? I and J again. Okay.
Negative sine t.
Okay, negative sine t, positive cosine t, 2, negative sine t, cosine t, and then
Negative cosine t.
right,
Negative sine 0.
and then repeat negative cosine t and negative sine t. Okay. Now we do our down diagonal, which gives us 0. Okay, then do this down diagonal, and that gives us negative 2 cosine t j. And this down diagonal will give us
Sine squared.
Sine squared tk. Okay, now let's do our up diagonals.
Plus cosine squared tk.
Okay, up diagonal there. I haven't thought ahead very well. What's that?
Plus 2 sine.
Plus 2 sine ti. Got them out of order, but it's okay. And then
0.
nothing. Okay? So what do we get when you put those two together?
2
You
sine
get
I
2 sine ti minus 2 cosine tj. Okay. Now,
plus
oh,
1
plus 1, plus k. Perfect. Okay, because that adds...
Pythagorean identity, right?
Yeah, right. And what that gives us is a vector that is perpendicular to both of those two vectors. Okay? Okay. Let's not do too much with it. All right, let's just see how they did it. Our r prime was minus sine t I plus cosine t j plus 2k. R double prime was minus cosine ti minus sine tj. C was 0, yes, and D was 2 sine ti plus minus 2 cosine tj plus k. Perfect. Okay? All right. Now, do we have how much time left?
4 minutes.
Huh?
4 minutes.
4 minutes. Okay, I think we have time for this next little slide. It's not going to be major. Yes, this is top of page 830. The parameterization of the curve represented by the vector value function r of t is equal to f of ti plus g of tj plus h of tk, we've seen that many times, is smooth on an interval I when L prime, G prime, and H prime are all continuous on that interval I, and the r prime of t is not the zero vector. That's a bold 0 there. It doesn't look like it, but it's supposed to be. In your book, it looks more like it's supposed to be bold. I think the graphing guy didn't realize there's a difference there. For any value t on that interval I, it cannot be, the r prime of t can't be 0 for any. Okay? That means no horizontal tangent lines. Okay. All right. Now, I don't think there's going to be time for example 3, is there? Probably not. Okay. You don't say that very quickly. Okay. So what we'll do is start with example 3 next time. And we made decent progress today. I think you can do any of the odds 3 through 9. You can check your concept check too. 3 through 9 on page 834, wherever, whatever. Well, they're all at Calc Chat. 5's at Calc View. Excuse me. And then any of the odds 11 through 17, they're all at Calc Chat. And I think you can do 19 or 21. They're both at Calc Chat. And I think you can do either 23 or 25. They're both at Calc Chat. 23 is at Calc View. And I think you can stop there, and we will pick up those after we do the next examples. Good deal. All right. Any questions?